Alright, in this video we're going to talk about the indeterminate forms, and this is necessary information to go over before we talk about L'Hopital's rule in the next few videos. And L'Hopital's rule is a technique that helps us evaluate limits that we otherwise can't evaluate or maybe need to use more complicated techniques. So here we're going to talk about what the indeterminate forms are. There are 7 of them. We're going to talk about what it means to be indeterminate and explain why they're indeterminate. So we'll just go ahead and list them in no particular order. So the first one we'll list is 0 divided by 0. Then we have infinity divided by infinity. And then we have infinity minus infinity. Then there is 0 raised to the 0 power, 1 raised to the power infinity, infinity to the 0 power, and then 0 times infinity. Okay, so what does it mean to be indeterminate? So if something is an indeterminate form, that basically means it has no numeric value. So if we say something like 8 divided by 2, we know that that has the numeric value 4. But something like 0 divided by 0, that does not have a numeric value. Just a sad face. Okay. Now why is that? Because we cannot have a 0 in the denominator. So even though we have a 0 on top, that still doesn't allow us to have a 0 in the denominator in the bottom here. Okay. So because there's a 0 in the bottom, this is an indeterminate form. So what about infinity divided by infinity? Well, we might be tempted to say, well, hey, there's something on top and it's the same thing on the bottom. So if we have something like 7 divided by 7, we know that that equals 1. But the reason that that works is because 7 is an actual number. Okay, infinity is not a number. So we might be tempted to say infinity divided by infinity equals 1, but that's completely untrue in general because infinity is not a number. Okay, so that's a very important point to keep in mind, and that actually explains most of these other ones here, pretty much all of them except for 0 to the 0. Okay, most of the rest of those are indeterminate forms because infinity is not a number. So let's go ahead and write that down just to make the point. So infinity is not a number. And I'm not writing in all capitals to yell at you, I'm writing in all capitals to emphasize the point here that infinity is not a number, so we do not want to treat it like one. So because we're not treating it like a number, then infinity over infinity is not 1. It actually does not really have a numeric value. That's why it's an indeterminate form. So if infinity is not a number, what is it? Well, it's pretty much just a symbol that represents an infinitely huge quantity that we can't really effectively measure. It's just a symbol that represents an infinitely huge quantity. Now, how about infinity minus infinity? Well, we might be tempted to say infinity minus infinity equals 0, but again, that's untrue for the very same reason. Infinity is not a number. We cannot treat it as such. So we know, for example, that 6 minus 6 is 0 because 6 is a number. It's okay to say that. Okay, but infinity is not a number. It's just a symbol that represents an infinitely huge quantity, so we don't necessarily know that infinity minus infinity is 0. Okay, it just has no numeric value. It's indeterminate. Now, how about 0 to the 0? So let's go ahead and clear some space here. Well, remember there are some rules from basic algebra. When you first learned about exponents, you learned some rules that said, well, if we have something like 0 squared, or, well, 0 squared is 0, right? 0 to the first is 0. 0 to the 7th is 0, and so on and so forth. So basically, 0 to any power a is 0, as long as a is not 0. Okay. Now, what about something like 1 to the 0? That's just 1, right? How about 2 to the 0? That's 1. 7 to the 0 is 1. 8.5 to the 0 is also 1, okay? So if we have anything, let's say b raised to the 0 power, that's always going to be 1 as long as b is not 0. Okay, so notice in both of these here, so we can have 0 as a base, and then if we take that base 0, raise it to any exponent that's not 0, we just get 0 back. We can have 0 in the exponent as long as the base is not 0, okay? So notice, if 0 is a base, we exclude 0 as an exponent. If 0 is the exponent, we exclude 0 as a base. So what happens then if we have 0, let's use a different color. What happens then if we have 0 raised to the 0 power? Well, according to this rule, it would be 0, except we exclude the exponent 0. And according to this rule, it would be 1, except we exclude the base 0. So 0 to the 0 really has no numeric value, just a sad face. So that's why 0 to the 0 is an indeterminate form. It has no numeric value. Okay. Now, for these remaining 3 here, it's pretty much for the same reason that we talked about with infinity over infinity and infinity minus infinity. Infinity is not an actual number, so we cannot treat it like 1. So even though 1 to the 0 is 1, 1 to the 7th is 1, 1 to any real number a is 1. Okay, but remember, infinity is not a number. It's a symbol that represents an infinitely huge quantity, so we cannot treat infinity like a number. So for that reason, 1 to the infinity has no numeric value. So it's an indeterminate form. Same thing with infinity to the 0. Okay, even though 1 to the 0 is 1, 2 to the 0 is 1, 7 to the 0 is 1, 8.5 to the 0 is 1, because 1, 2, 7, and 8.5, those are all numbers. Infinity is not a number, so we can't treat it like 1. And last but not least, 0 times infinity. Okay, 0 times infinity has no numeric value because, well, we know if we take 0 and multiply it by any number a, we're just going to get 0 back. That works because this a here is a number. Infinity is not a number, so we can't treat it like 1. Okay, that's a really important point to keep in mind there. So because of that, 0 times infinity has no numeric value. It's an indeterminate form. Okay. Now, what's so significant about these indeterminate forms? Well, if you're evaluating limits, the first thing you always want to try is direct substitution. And if you do direct substitution and you get one of these 7 indeterminate forms, then that tells you that you can use L'Hopital's rule. Okay. So in the next few videos, we're going to see some examples of using L'Hopital's rule when we get these indeterminate forms. And what's nice is if we get 0 over 0 or infinity over infinity from direct substitution, we can use L'Hopital's rule right away. But if we get one of these other 5 here, then we'll have to do some algebraic manipulations first to eventually get us into a point where we can use L'Hopital's rule. But the main point here for this video is just to cover the indeterminate forms, talk about what they are, what it means to be indeterminate, and why they are indeterminate. So L'Hopital's rule coming up in the next few videos.